All right. Thank you, Beth. And thank you to everyone here today for joining us for this introduction to the Lake Loading Response Model, or what we'll be calling LLRM for probably the remainder of the presentation. So I'd like to just start with a quote here from Otto von Bismarck, which is the way I think most presentations really should start. But that is, to retain respect for sausages and laws, one must not watch them in the making. And I'm adding up here that this also applies to water quality models. So welcome to a tour of the sausage factory. And also extra points for anyone who noticed that Otto was wearing a Secchi disc emblem here and on his hat. So our agenda for the day. So three major parts of this webinar. So the first one I'll be leading. So that's just kind of an overview of limnology concepts for modeling. My colleague Dave Roman will be picking up on parts 2 and 3, which are an overview of approaches to modeling, and then part 3 being getting into the weeds on lake loading response model in more detail. So for the next 45 minutes or so, I'm really just going to be Dave's opening act, and he'll be taking on most of the heavy lifting and training on LLRM. So before we get into that, what is lake modeling? Why are we here? Why is anyone even interested in any of this? So lake models use available information to help explain and, importantly, to predict how lakes behave. That includes how they might behave in the future in response to changes in land uses. Models can inform lake management decisions and help answer questions such as, how much pollutant load do we need to reduce to meet our water quality goal? Where within a watershed would lake management funds be best spent to prevent algae blooms? You're sort of targeting those hotspot areas, figuring out where to spend your money. What will lake water quality look like in 25 years or 50 years? How much will lake water quality improve if a sewer system is installed? How will a lake respond to climate change? So these are the kind of things, really we're trying to create a construct that lets us project into the future and understand how the lake responds to changes in its watershed. So with that, we'll jump right into limnology concepts for modeling. And we'll start with talking about lake physical and morphological features. So in terms of what we're going to talk a bit about different types of lakes and how they behave differently in terms of the modeling perspective we're trying to set up here. So first up is glaciated lakes. We have a lot of these, at least in the northern tier of the US. So about 13,000 years ago, plus or minus, the glaciers retreated off the landscape, leaving these big chunks of ice that, as the glacier continued to melt, left this outwash of glacial till that then surrounded the chunks of ice, eventually subsiding and leaving these essentially holes in the ground that are our lakes now. This can vary quite a bit, but this is just kind of a conceptual framework. So from big to small, you can have, on this example on the left, this is Newfound Lake in New Hampshire. Pretty good sized lake. You can see there's some deep holes here pushing over 170 feet of depth. So it's a good deep lake. On the other end of the spectrum, here's Ponema Bog, also in New Hampshire, very shallow and acidic, as you would tend to expect in a lot of bogs, but both have glacial origins. So wide range of potential outcomes. But in general, you're looking at holes in the ground created as a result of glacial retreat. Other types of water bodies you can apply modeling to. Different types of reservoirs and impoundments. So here is Pondcook Reservoir. It's a very riverine impoundment. So that, kind of a snaky channel-like aspect to it. You got a bit of impoundment here, it kind of widens out on the downstream end, but it still maintains a lot of that riverine characteristic and a rapid flow through, a lot of turnover in the basin. Different example that looks more like the bigger glacial lake we just looked at is here. Big earthen impoundment, sort of classic reservoir type scenario. And then on the smaller end of the spectrum, you've got beaver ponds. So these are equally applicable to the lake loading response model, but we'll get into some of the details about why understanding the flow characteristics are very important to predicting water quality. And then just a few others just for fun. We've got oxbow lakes. This is an example of where a river just doing its natural tendency to change over time. Here's an old river bend that just got tighter and tighter over time. And then at some point, it got so tight that during a big flow event, it jumped the banks and carved out a brand new channel that was just an easier flow path. And you can see there's a few here, a few oxbows that were remnants of the old river flow channel. If you ever look at an aerial of a big river system like the Mississippi, look down in the Delta, it is just an endless collection of these oxbows. And a few others, just esoteric ones. This one here is in Quebec. It's created from a meteor impact and an upwelling in the middle after the initial pushing down of the earth subsided. So you've got this ring-like effect. And then in terms of having the tiniest possible watershed, this is Crater Lake in Oregon, really a watershed that only goes up to the crest of the volcanic crater here. So next concept up is thermal stratification. So when we're talking about deeper lakes, they generally have 3 different thermal zones in the summer. So at the top, we've got what's called the epilimnion. Those are the surface waters. This zone of the lake is well oxygenated by wind, waves. Even a good-sized motorboat can do a lot to stir up and keep that top layer, really well oxygenated. In the middle, we've got this zone of rapid change, where both dissolved oxygen and water density rapidly changes. And because of that rapid change in density, it actually creates a mixing barrier between the top and the bottom. And then down at the bottom, the hypolimnion, this is an area of deeper lakes, which, if deep enough, they can be aphotic, meaning light does not penetrate. Light will get sort of diffracted out by hitting bits of suspended sediment or even algae particles in the water. So that light gets diffracted and doesn't fully reach the bottom sediments. These bottom waters in the summer can often go anoxic, and that's important. We're going to talk about that in a little more detail later, of what can happen when the bottom sediments of the lake, as they're separated from the top. So imagine you've got this barrier. So there's a compartment down here that's kind of blocked from getting all this good oxygenation that's happening at the top. Sediment that's at the bottom of the lake will continue to decompose. The water's not so cold that decomposition is halted. And decomposition consumes oxygen. So these bottom waters can get lower and lower in oxygen over the course of the growing season. So we'll talk a bit more about that later. So in terms of the watershed, lake and watershed nutrient dynamics, meaning how do nutrients get into the lake and how do they exit the lake? We've got a bunch of different ways that can happen. So nutrients can get into the lake just by way of what we call dry fall or aerial deposition. So this is constantly happening even when it's not raining, just very slow, steady rate of deposition coming right out of the sky as a result of prevailing wind patterns. This is just something that happens all across, all types of terrain, not just lakes. We've got tributary inputs. So these are the inputs that are coming down in the water of a river or stream system. You've also got stormwater runoff that's directly flowing over the land. So with different degrees of pollutants that are being delivered to a water body, depending on land use. So you can imagine there's a different rate of runoff for pollutants right after a farm field has been fertilized as compared to a low density residential area with grass lawns as compared to forest. Each one has kind of a predictable range of nutrient and pollutant discharge from overland flow. Other things to consider are septic systems in the nearshore area. Generally speaking, when we're trying to calculate loads from a modeling perspective, loads from septic systems, we're looking at septic systems that are located within a 200-foot radius from the shore. There's a little bit of plus or minus on that depending on the soil types, but 200 feet is a pretty decent rule of thumb for getting a head count and doing the math on the loads coming from septic systems. You've also got stormwater that infiltrates into the ground and makes its way into a lake through groundwater input, and that also will be an exit from the lake by way of groundwater. Some of these sources of nutrients and other pollutants will get buried, meaning they'll become incorporated into the bottom sediment and buried at a depth where they're no longer biologically available. So this is where we come back to that concept of thermal stratification and what's going on in the hypolimnion during the summer. So I mentioned that decomposition. We've got aquatic plants and microscopic plants, which are phytoplankton, microscopic algae. Those will settle down to the bottom of the lake and decompose. When you get to that point in the summer where decomposition has been going on long enough and the oxygen has been being consumed long enough that dissolved oxygen levels start to approach zero. So once you get below 1 milligram per liter, you start getting into that danger zone where nutrients, or phosphorus rather, that are bound to the sediments, they're actually locked onto the sediment and not biologically available for algae. There's a chain of events that happen chemically that then re-release that phosphorus in soluble form right back into the water column where they can become food for algae. So that's what we call internal load. And it's really important to understand and put a number on that internal load when we do lake modeling. So to play that concept out a little bit more, for a geologically young lake, or what we call an oligotrophic lake, this is sort of the natural progression over the course of a growing season of different types of algae. So the diatoms here, those are the larger celled golden brown algae that tend to be at their peak right after the ice comes off in the spring and through the early part of the growing season. Then around May and into the middle, early part of the summer, the green algae take over and reach their peak. Then the blue-green algae, also known as cyanobacteria, they reach their peak around August, and then going back in the fall to having the diatoms take the lead and peak again. So this is just a very general construct for a geologically young lake that is not very organically or biologically productive. For lakes that are a little further along in the aging process, and we'll talk more about this in a bit, this is what happens. You see the same pattern of diatoms to green algae to the blue-greens and back to the diatoms, but when you've got internal loading really happening at a high rate in these lakes that have more and deeper organic sediments, that pulse of nutrients from internal loading back into the water column is happening at just exactly the wrong time. So these blue-greens, the cyanobacteria, some species of those contain liver toxins or neurotoxins. And when they die back and the cells break up, they can release those toxins into the water. And that becomes a health threat to humans or to pets that might drink the water. Can cause a variety of health risks. So it's that progression, but also it's the teeing up of the blue-greens and that release of internal load phosphorus that is problematic because it's happening at just the wrong time of year. So how do lake types differ? All sorts of lakes, as we've talked about, big, small, and different features, kind of like think about how different dogs can be. You get Dachshund here and this much larger dog. So some general concepts. So glaciated lakes tend to be deep relative to their area. So here's just kind of a look of a cross-section of a glaciated lake with two true deep holes. The darker blue represents deeper water. So we get a deep hole in the north, a couple of deep pockets here, and a true deep hole in the south. So generally deep, a lot of water volume relative to the size, the area of the lake. On the opposite end of the spectrum, reservoirs in general, and this varies quite a bit, so this is just a very general rule, they tend to be relatively shallow for their given size in comparison to deeper glaciated lakes. Please do not put your dog in a frying pan. This is for representation purposes only. NEIWPCC does not condone the frying of dogs. So again, why is depth important? So New England lakes are typically what we call demictic or polymictic. So demictic lakes are those deeper, typically larger lakes that mix fully, meaning the top waters and the bottom waters fully mix twice per year. And that is in the spring, right after ice off, and in the fall when the temperature of the water, the air temperature gets cool enough that the surface waters cool and they equalize with the bottom waters, and that allows full mixing from top to bottom. So that's true for deeper lakes and ponds. Polymictic lakes are the lakes that are shallower, and it's that shallow depth that allows them to mix often many times per year. A big wind event can be enough to mix up a shallow lake. And that's mixing from wind and wave. And as I mentioned before, even a high-powered outboard motor on a boat can be enough, in some cases, to mix a lake from top to bottom as it's moving around. So just an example here of some of the math that goes into a model when we think about water volume. So one of the things that we're concerned about that's really influenced by volume is residence time. And that's the concept of how frequently does all the water sitting in the basin of the lake get completely replaced by a new volume of water from the watershed. So in this conceptual construct I've got here, imagine 3 lakes of exactly the same volume. So in this case, the unit of 100 could be whatever you want. It could be 100 cups of coffee worth of volume. It could be 100 million gallons. It's just to represent that these 3 lakes are all the same size. So in this case, if you've got an inflow of 50 units and a volume in your lake of 100 units, so inflow is always going to equal outflow. In this case, the inflow is half of the volume of the lake. It's going to take 2 years to completely exchange the water in that lake. So if we jump down to the bottom scenario here, we've got the same size lake basin, but a much larger watershed. So now we've got 200 units of inflow for 100 units of volume in the lake. That lake is going to get completely replaced or turned over in a half a year. So this is the kind of math that we need to do to understand and to construct a model of the lake. Has a big bearing on water chemistry. So just a few examples of what kind of a range this actually exists in the real world. So up top, we've got Bantam Lake. It's the largest natural lake in Connecticut. So pushing 1,000 acres. It's not too deep for a lake of that size. It's only 24 feet deep at its maximum. So it has a residence time of 0.3 years. So just a couple of months before the entire lake volume is replaced. So in this case, big watershed, relatively shallow lake, and it's flushed out, multiple times per year. Moving down to the middle, we've got Sebago Lake, which is the deepest lake in Maine. So 29,000 acres, quite a bit deeper than Bantam Lake. It's 316 feet at its deep hole, and it has a residence time of 5.4 years. So that's quite a bit of difference. And then on the far extreme, this is Lake Tanganyika, which is the deepest lake in Africa, 8.1 million acres, maximum depth of almost 5,000 feet, residence time 5,500 years. So we don't have anything like that here in New England, but just to kind of make the point that residence time can vary a lot based on watershed size and depth and so on. So residence time also influences how much sedimentation can occur. So the longer the residence time, the higher the settling rate, more material settling at the bottom. So think about a tributary coming in this case, after a storm event, you've got some sediment-laden water coming down the tributary, reaching the lake. When sediment's being transported in a riverine system, the flowing river has a lot of energy. The velocity of the water gives it the energy that it needs to transport those particles. As soon as it hits the open water, that energy is lost. It's almost like you're carrying a big rock and you just run out of steam. You just can't hold it anymore, so you drop it. That's what happens here. The river is providing the energy to carry those particles. It hits the lake. The energy is lost because there's no more flow, and that's why you have these sediment deltas occur at the mouth of rivers. And the sediment is often a transport vehicle for nutrients that are attached to those sediment particles, and that's why we're concerned about it, in addition to the loss of depth, which is obviously an impact to a lake. So from a modeling perspective, another thing we have to consider is not just depth, but also depth in the context of the shape of the lake. So that will tell us how many modeling units we really need to be considering. In this case, again, of Bantam Lake, this is, again, that biggest natural lake in Connecticut. We had some choices to make in our model here. We could see that the North Bay was kind of like its own little world up here, connected to the center of the lake by a neck, but it was a pretty wide neck. It was a big, broad opening, no real constriction of flow. And then a South Bay down here, but again, very broad opening. So after looking at it, and seeing that the depths were not radically different, from one bay to another, and looking at the size of that opening and there really wasn't that loss of energy or a constriction that would change the transport of sediment or flow of water from one bay to another. We made the judgment call that this was the type of lake that really needed to be modeled as one unit. On the other end of the spectrum, over here, we've got Lake Cochituate, which is in Natick, Framingham, and Wayland, Massachusetts. Three very distinct basins. So water flows from the south to the north. The South Basin is kind of set aside in this, the box over here on the left, but it's got a true deep hole, shallower at one end, shallower down the other end. It hits Route 9. This is at its northern tip. So that's this part of the map in the inset. You go from shallow to another true deep hole, back to shallow, a constriction at the Massachusetts Turnpike, up to the North Basin, where it hits another true deep hole on its way to the outlet. This is a classic example of a lake that has one name. All three of these basins together are called Lake Cochituate, but from a modeling perspective, they really should be modeled as three completely separate lakes, with flow, with water quality conditions and flow and transport being modeled separately for each basin as a contributor to the one that's downstream. All right, so now we're going to talk about lake trophic classes. So I'm starting here with a picture of Iceberg Lake that's in Glacier National Park. So this is sort of like a classic example of a geologically young lake. In this case, the glaciers have retreated not really very long ago. There's still active glaciers very nearby, and this picture was taken midsummer. So you can imagine that once you get into the water, you get very coarse mineral type substrate, rocky, sandy, not a lot of organic material at all, not a lot of organic anything in there, plants, fish. It's not very biologically active. So it's geologically young, and it checks all the boxes of what we would call a geologically young or oligotrophic lake. So eutrophication is the term for the natural aging process for lakes. So, and it's important to remember, this is a natural process that every lake goes through. It's the gradual accumulation of organic matter and sediments from the watershed, resulting over time in decreased depth and increased biological productivity. That is not to say that this process is in any way bad. There's no value judgment about this. We do get concerned about it as lake managers when this process is really accelerated by human activity in the watershed. So as in general terms, this aging process should take thousands, or in some cases, tens of thousands of years to go from oligotrophic to mesotrophic, to eutrophic. But in watersheds that are heavily developed and where we've got a lot of homes, septic systems, and other heightened sources of pollutants, we can be talking about this process in terms of decades rather than thousands of years. So these little graphics down here, just giving a shout out to ChatGPT as being really, it's the highest and best use to create slides using ChatGPT. Now is the first time I've used this slide, and now I can tell people that mesotrophic lakes, but when your lake is in this zone, that's when it starts wearing cheater glasses and starts complaining about keeping kids out of its yard. So what are the primary factors that affect trophic state and that natural lake aging process? So the first is the rate of nutrient supply. It's kind of like the diet of the lake, and the same nutrient supply will affect different lakes differently. It's going to depend on a lot of the features that we've talked about already. How big is the watershed? What types of land uses are happening on that watershed? I like to make the analogy that it's sort of like if I ate a supersized McDonald's meal every single day and my 18-year-old nephew did the same, our bodies would respond differently because we have different metabolisms. It's the same thing with lakes. So part of what modeling does is it lets you understand the metabolism of the lake. What is the relationship between the input of nutrients and the in-lake chemistry that results from that? Second will be climate. So in simplest terms, this really just kind of gets down to growing season, temperature. As the climate gets warmer, we're going to see on the margins maybe a few extra days of growing season in the early part and a few at the end. And it's going to happen slowly over time, but it does affect biological productivity and trophic state. And then we've already talked about this, the shape of the lake basin, morphological features like depth, volume to surface area ratio, and watershed to lake area ratio. So when we think about trophic state, there are a lot of ways to measure that. I'm just going to talk about one of the simplest and most commonly used metrics, and that is the Carlson Trophic State Index, or TSI. So the Carlson TSI looks at three parameters, total phosphorus being the most important. This is what we call the causal nutrient. Phosphorus is typically the limiting nutrient for plant and algae growth in fresh water almost all the time. So by limiting nutrient, we mean there are a lot of nutrients that are important and absolutely necessary for plant and algae growth, but phosphorus in that cookbook of things of what plants and algae need, phosphorus is the ingredient that's in least supply. So as we increase the supply of phosphorus, we will increase algal productivity and plant productivity. So as we increase algal and plant productivity, we see a rise in chlorophyll A, which is the next parameter on the list. This is what we call a response variable. So chlorophyll A doesn't increase on its own. It increases because the source of nutrients, total phosphorus, has been increased. So what is chlorophyll A? It's a photosynthetic pigment that's found in all plants, including the macroscopic rooted plants and the microscopic algae, and in cyanobacteria, the blue-green algae. And then finally, water clarity, Secchi disk. This is another response variable. The Secchi disk is a really simple tool that's used to measure water clarity by taking this sort of like this disk that's about the size of a pie plate. It's got black and white quadrants on it, and it's simply just lowered into the water to the point where you can't see it anymore. And you can use that as a comparative measure to compare clear lakes to less clear lakes. Light is diffracted, as I mentioned before, by sediment particles in the water and algae. So in this picture here, you can see how those little bits and particles are diffracting light and starting to obscure the Secchi disk. So without getting into too many details on this table, we have numeric ranges for each one of these parameters that will peg us or peg a lake as being oligotrophic, mesotrophic, or eutrophic. So one important thing to keep in mind about this index, this is showing those parameters and their data ranges on a logarithmic scale, so they're all kind of normalized and you can look at them together. You really should, it's a common mistake to average the results of these three variables. You really want to look at them independently. Sometimes funny things can happen where transparency and total phosphorus line up really well, and they both will tell you, okay, this is a upper mesotrophic lake, or it's a mid-eutrophic lake, but then the chlorophyll A will be way out of whack. And it's always interesting when you find one parameter that's out of sync with the other two, and that forces you to dig a little deeper on the data and really understand what's happening in that system. But it's just a reminder that it's important to look at each variable independently and not average them. So where do nutrients come from in a lake watershed? So this is a kind of a very simplified view of land uses in the pie charts here of land uses in the Bantam Lake watershed. Just for simplicity and ease of viewing, we've grouped a bunch of land uses together. So you'll notice in the pie chart, orange is described as urban land. In this case, urban land is looking at really all types of residential use and the Bantam Lake watershed on the map over here is not what anyone would consider an urbanized watershed. It's not heavily developed at all. There's no cities in there, but this category sort of represents residential land use and other human type land uses. So the main message here is that you've got a predominantly forested watershed. So 62% of the watershed is forested, but that forested land only comprises about 35% of the total discharge of phosphorus to the lake. On the other hand, you've got a combined 20% of the land, which is urban or agriculture, but together, urban and agricultural land uses comprise over 50% of the nutrient load to Bantam Lake. So it's just kind of a reminder that land uses can help focus where you can actually make a change. You're not going to improve the runoff condition in a forest, but you can improve it in urbanized or agricultural lands. So it's just kind of give you a relative sense of how a given land use can have an outsized impact on loading to a lake. So once you've understood the land uses and have some modeling tools like you get out of LLRM to estimate what the loads are from those, we start thinking about concepts including nutrient attenuation. So that is really thinking about how do nutrients work their way from the source down to the receiving water. So very simplistic model, but helpful, I think, in just thinking about this. So we've got five sub-watersheds that are color-coded here, going from the headwaters here at W14, and then flowing down, eventually reaching Bantam Lake here at the southern end of the figure. So as a conceptual model, just imagine that each one of these sub-watersheds had a load of 10 kilograms per year of phosphorus. They're different sizes, different shapes. In the real world, they don't all have the same load, but just for sake of discussion, let's just say 10 kilograms for each one of them. So down here, you can see, if you do the math, 5 sub-watersheds delivering 10 kilograms per year, you get a total of 50 kilograms. But that's not how it works. As waters flow from the headwaters and work their way through the system, there's a loss of some of those nutrients that gets grabbed in wetlands. There's vegetative uptake that happens. There's settling and burial of some of those sources of pollutants as they flow through the system. And the amount of attenuation is going to vary quite a bit depending on the features that you have on the land. But we've made it, again, a very rough conceptual model here that says that for each one of these sub-watersheds, we're going to have a 10% removal, okay? So instead, up here in the headwaters of having an actual load of 10 kilograms per year, with attenuation, that drops down to 9 kilograms per year. So as you work your way through the system, you can see here on the right how that starting point of 10 kilograms from the headwaters gets reduced by the time it actually reaches Bantam Lake. So by doing that simple math, and applying that factor of 0.9, meaning 10% of it's removed on its way as it flows down through the system, our starting point of 50 kilograms total for the whole of these 5 sub-watersheds gets reduced to 36.9 kilograms. Now, in LLRM, as Dave will get into later, you've got to make some professional judgments. You're not going to just assign a 10% removal factor to every watershed. You're going to have to really look at the landscape. How big and broad are the wetlands? What other features do you have on the land? What kind of slopes do you have? So the attenuation range that you will decide with professional judgment will range from 10% up to 60% removal. That's sort of the generally accepted range that's applied. So other considerations. What kind of data do you need to feel confident to move forward with your modeling and your calibration of the model? And that's not an easy question to answer, and we're not going to, we could spend an entire 3 hours just talking about statistical methods for data, but we don't have time for that now, so I'm going to give you the real lightning tour 2-slide overview. So how many samples do you need to take at least a crack at using your data from each sampling point? And the answer is, it depends. So a single sample, you go out there once, you grab a sample or two, that's really not enough. You need a systematic approach. Hopefully you can get out there on multiple dates with all of your sampling from different stations happening at a relatively, same time of day, meaning you don't sample one site on one day and then come back 2 weeks later and take a sample from another site after there's been, 10 days of rain in between. You want to have some consistency in the timing. So bottom line, from a statistics perspective, at any given sampling point, you need at least 11 samples. That is the very rough rule of thumb before you can start talking about averages or even looking at other statistical measures like medians. There's always better to have more data. What you're going to find, though, often with modeling is that you're not going to have a perfect data set. It's almost never that you have a perfect data set, and you've got to make some choices. So as a general rule, 11 is sort of like the beginning entry number, at which point If you got less than that, you really ought to think about getting some more sampling done before you're using that sampling site in your model. I already mentioned this. You want to make sure that your sampling is done, in a shorter time frame as possible to kind of iron out variations in discharge, weather, changes in water temperature, and so on. And do it in a short period so you're not comparing apples to oranges. So one of the reasons that data analysis is done on water bodies and the modeling is done in conjunction with that is that you want to be able to look at where you are with water quality and have a sensible way of setting some water quality goals. Without modeling and an understanding of the relationship of the watershed to inlet chemistry, you're kind of standing in a dark closet. I mean, you can set a goal. You might say, well, we're at 28 micrograms per liter in the middle of the lake during the summer. Let's try to get down to 20. But you really won't know how much work it's going to take to get there, how much phosphorus load reduction you need to get there. So it's important to have a model and have good data to set your goals. So when you think about goal setting, I like to think about it as sort of a Goldilocks type challenge. You don't want to be too extreme, set a goal that's not realistically attainable. So an example of that would be to set a total phosphorus in-lake goal that would be more in alignment with a completely forested watershed with no human development. You're not going to ask people to tear down their homes and then tear up all the roads in the watershed. So you really shouldn't be thinking about setting goals that are not realistically attainable. On the other extreme, you might set a goal that's not protective enough. So that goal may be achievable, but it's not going to prevent the water quality impairments that people in the watershed may be concerned about, like nuisance algal blooms. So in a perfect world, you want to set a goal that's both realistically attainable and conservatively protective of lake water quality and preventing impairments. Keeping in mind that you're probably going to need to go back and revise that goal as needed. See what happens over the next 5 years, 10 years as you're trying to make improvements in the landscape and building stormwater improvements to reduce pollutant loads. This is the concept of adaptive management. So the idea that just because you set a goal doesn't mean it was right. It means that you're going to have to constantly be, reevaluating it based on new data and based on changes that you're making in the watershed, and as land continues to be developed. So that's sort of the Goldilocks approach. So just a few really quick examples of how this can play out. I know these are busy slides, so I'll try to make it simple. The first example is Mirror Lake in Tuftonboro. So this is a lake that had pretty good water quality. They were within the mesotrophic classification in the state of New Hampshire, which is between 8 and 12 micrograms per liter. They were right kind of smack in the middle of that. They had a median of, their current lake median was right at 10, so exactly in the middle of the New Hampshire mesotrophic class. The goal that was set was a group process with the state agency, with the Lake Association, and others, town employees. They set a goal of 8.5 micrograms per liter. And in that watershed, that required a pretty modest load reduction of only 7.4 pounds of phosphorus per year. So it checked the box of being conservatively protective. This goal would put their water quality right on the low end of the state mesotrophic range. It was realistically achievable, meaning they didn't have to reduce their watershed load by 80% to reach it. It was a modest amount of reduction. And it was consistent with the state trophic standard that lake was put into. Here's an example of how things can go wrong. So Lake Warner in Hadley, Massachusetts had a modeled predicted total phosphorus level of 120 micrograms per liter. No in-lake data to back this up, but the TMDL that was written for this lake at the time was going off of a modeled average only. The TMDL cited 40 micrograms per liter as the water quality level required to maintain 4-foot Secchi disc clarity. And the rationale for that was that 4-foot Secchi disc clarity was the bathing beach standard. However, there are no swimming beaches on this lake. It's not that kind of water body. So basically, to make a long story short, a water quality goal of 30 micrograms per liter was not really conservatively protective of the water body. It really wouldn't prevent, expectation of algal blooms and high productivity of aquatic plants. That goal was not realistically achievable based on the data that we had. You're up here looking at a prediction of 120 micrograms per liter. Realistically, there was no reason to think that you're going to get to 30 anytime in anyone's lifetime. And it wasn't consistent with state water quality standards because the ones that were being cited weren't really relevant to this particular lake. So this is a case of a goal setting that had kind of gone off the rails a bit. And then the last example, we're coming back to Bantam Lake in Connecticut. So the lake, based on the data that was available, had an in-lake phosphorus concentration of 24.7. State of Connecticut had the mesotrophic range for its state ranging between 10 to 30 micrograms per liter. So the lake's kind of in the mid upper end of that range. So a target was set to reduce from 24.7 to 23, which would put Bantam Lake at the lower end of the state's mesotrophic range. So it was an 8.6% reduction in total phosphorus. So was that goal consistent with state water quality standards? Yes. The questions are, is it conservatively protective? Is it realistically achievable? At the time of that goal setting, the answer is we don't know because the data really was not sufficient to feel confident about that. So sometimes it's important when you're doing this kind of planning and modeling to just move forward with the data that you have, but have a big caveat, that everyone understands that, this is the best we can do right now, and we simply need more data, and we're going to look at it again in 5 years when we've got that data to play with. All right, so with that, I think we're going to take a pause and take some questions, and then Dave will be picking up with an overview of modeling approaches.
Great. Thanks, Bob. We have a few questions in the chat. I'm going to go ahead and read those to you. Okay. So here's one. Do you estimate the lake inflow based on watershed and annual rainfall, or must you measure outflow?
It can be done a number of different ways. It's probably most often done the first way, looking at, estimates. I mean, it's great if you've got a gauging station and you can get really dialed in on actual data, but you can model it based off, the watershed land area and slopes and soils and that kind of information.
All right. To what extent does phosphorus dissolved in groundwater get attenuated?
Ooh, that's a great question, and it varies a lot based on soil type. That's sort of that's the best short answer that I can give. That's a very tricky one. This question comes up a lot when you're trying to really get a refined estimate of contribution of septic systems from the nearshore area. And all I can tell you is that the literature is all over the place on this. And unless you're going to get out there and do some very site-specific soil investigations, it is tricky at best. But it very much depends on soil types.
Thanks. And another question or comment, I'm curious if there are any references you could provide to help determine the attenuation factor for different landscapes or watersheds.
I'm sorry, Beth, can you repeat that question?
Sure. I'm curious if there are any references you could provide to help determine the attenuation factor for different landscapes or watersheds.
Yeah, I mean, again, this is going to vary quite a bit, and it is one of the trickier parts, or it's one of the parts of modeling that does require the most professional judgment. And I think maybe, Dave, if you want to tag team with me on this, to some extent, so you're working off of the literature, what the low to high end of the typical range is. And in most cases, the best thing that you can do is hopefully you've got monitoring data scattered around your watershed enough, meaning you've got it in lake and you've got it for tributaries, in locations that allow you to take the modeled estimates and then calibrate them with field data. So you can kind of look at what the gap is between what the model's predicting and what the actual data is telling you, and then turn the dials on the model. And Dave's going to get into the details on that later. I'm not sure that I'm answering this fully. And Dave, maybe you want to like jump in with a little more nuance if this is the right time to do that, or you want to save that discussion for later.
Yeah, I mean, Bob, I could just give like the one sentence on this, that if you're just looking for literature, the leak load and response model has a user guide that has a lot of good references and includes some of those ranges. So just that's probably the easiest starting point to look into that question. And I will share a link to where you can get all of that in the upcoming slides.
Perfect. Why do you use only septic systems within a short distance, given that phosphorus is a conservative pollutant?
Well, this gets to the previous question about, transport of pollutants through soil. This, in general, the ability for phosphorus to get bound to sediment and kind of get locked up there, as opposed to being pushed through the sediment eventually, or the soils rather, and work their way into the lake. Once you get beyond 200 feet, that's sort of like the conservative outer edge of what the literature kind of describes as being the zone where you're going to see that transport happening in a way that you can put a good number on. Is it possible for septic system 250 feet away to be contributing to a lake? Absolutely. Are there cases where you're at 190 feet and it's really not going to have a measurable impact? Sure. This is one of the things that once you get into modeling, there are a bunch of places where you're going to have uncertainty, and unfortunately, in order to use these sort of high-level models, you're just going to have to roll with the uncertainty. The alternative is to get into a site-by-site assessment. Looking at each septic system, how frequently has it been pumped out? How many toilet flushes per year are happening in each one of those systems? Is it a family of 7? Is it a single person living in that house? Really, ultimately, all of this comes down to the location of the systems, but also how many toilet flushes are happening per year. And that is very much, and the age and how well functioning that system is. It is very much a case by case. You're either going to do it site by site, case by case, or you're going to have to take a very high level kind of like averaging approach based on understanding of how many systems are within, whether you pick 100 feet, 200 feet, 300 feet. There's always going to be some plus or minus when you're doing septic system estimates.
Perfect. Here's another one. Regarding the number of samples, does it matter if it's 11 samples in a season, like every week in the summer, or 1 sample a year for 11 years?
That's a great question. I mean, I think that for the purposes we're talking about today, either one would check the box. You generally, when you're building your model, you do want to make a decision about what the timestamp is going to be on that data, both in terms of how many years you're going to look back. So if you take the idea that lakes will change over time in response to land development and so on, and just the natural aging process, you want to make sure that you're not comparing data from 2023 to 1978. So very often what we will do is we'll use 10 years as where we draw the line. We'll go back, we'll take the most recent 10 years of data, hoping that there's enough to work with. If there's not enough to work with, sometimes we'll stretch that 10 years out a bit, but 10 years is a good rule of thumb. Also, when you're using this model, you want to make sure that you're not comparing December data to mid-August data. So we'll try to look at data from the last 10 years and data from the summer period. What you decide that summer period is a little bit flexible. We'll often use like May 24th to September 15th, or Memorial Day to Labor Day, with a little plus or minus depending on what summer, whether you're in Maine or whether you're in Kentucky, you might pick a different date range. But in general, if the 11 points of data that you just described are spread out over multiple years and they're all in the summer months, great. If you get them all from the summer months within the same year, that's also acceptable.
Thank you. Is it realistic to set a reduction goal that is less than 1 microgram per liter difference from the current in-lake phosphorus, considering lab detection limits are not that precise?
Hmm.
And that was, sorry, that was the Bantam Lake example.
Yeah. I think, I think I'm comfortable with that. I mean, you are gonna have to accept, the limitations of your laboratory data. But over the course of time and over the course of, hopefully pretty robust data set, I do think that those medians are going to play out, and you are going to see a signal that can still be within that 1 microgram per liter range.
Okay. And so based on your experience, what range of percent nutrient reductions from watershed loading is realistic to achieve?
As a percentage reduction, I mean, that depends on a lot of things. It depends on the degree of development in the watershed. It depends on the time horizon that you're thinking about. If you're talking about, how much can we reduce in the next 5 years, that's going to be a different answer than what we can reduce over the next, 100 years. Thinking about it generationally rather than, well, let's just see what we can do, in the next 5 to 10 years. Often the, watershed planning is done with, at least in my experience, you're looking at a relatively near time horizon, meaning we set a goal, we write a plan, and we try to figure out what the low hanging fruit is. What projects can we do with the next funding cycle, meaning like within the next 3 years. And then everything else on the list will be like, once we've completed that top list of things, we'll just keep moving through the list. There are a lot of lakes. I mean, I've done watershed planning for urbanized lakes where you can set a goal and have it as a conservatively protective goal that's sort of like really aspirational, but you have to think about it in terms of like you're not going to live to see that ever happen. As long as you have a long enough time, planning horizon, a bigger goal might be okay to set. It kind of depends on a lot of things. It depends on politics. It depends on funding. It depends on how much development pressure you expect in a lake watershed. Some places a watershed may be nearly built out. In other places, there may be really, really extreme development pressures in the next 10 to 20 years. So I know that's kind of a fuzzy answer, but this is not a one size fits all type situation. It's going to really depend on the features of that watershed.
Thanks, Bob. There's a number of questions racking up here, so I'm going to try to get a couple more in before I think we were shooting for about a 2 o'clock break, so maybe a few more minutes for questions.
Sure.
Okay. Here's another. How do you correlate these concepts to predicting harmful algal blooms in a current season?
So that's actually the prediction of algal bloom frequency is actually built into LLRM. So I think just in the interest of time, I'll leave that for later because that is actually built into the structure of LLRM.
Okay, great. And you might have touched on this. How is internal phosphorus loading estimated for use as a model input?
So that is always kind of a gnarly question.
Hey, Bob, we have about like 5 slides on that, so I'd say we can save that one for later as well.
Okay, fair enough.
Because that's definitely a gnarly question.
Yep. So that can leave everyone in anticipation, but yeah, Dave will get to it.
Awesome. When the lake is stratified and the epilimnion and hypolimnion are physically separated, is it correct to assume a whole water body volume when estimating residence time?
Yes, because we're talking about the top to bottom exchange of nutrients, basically from a modeling perspective. But the inflow matching the outflow, I think I understand the question, but I think the general answer is yes. Yes, you can.
What impact will the 2021 EPA 304A criteria for ambient nutrients in lakes and reservoirs that was based on new understanding of these endpoints have upon target setting compared with the older TSI approach that was presented?
I think, the regulatory environment for goal setting is always important. In my experience, I've more often been looking at state water quality standards, which are more stringent than anything that's been promulgated by EPA. But beyond that, I find that even more often, it's not the state or federal standards that are driving the bus when you're doing goal setting. It's often a more locally driven, more conservative number that's chosen. So simply meeting a state or federal water quality standard, that might be something that drives the bus if you're writing a TMDL, like at the state level. But very often, watershed planning efforts have a local component, watershed association, watershed group, and they want a higher standard. Their standard might be, okay, great, we'd like to be meeting state or federal water quality standards. We also never want to see cyanobacteria blooms, so we want to be more aggressive about it. So it's factoring in both, what those local groups, the folks who live around the lake, are experiencing and what their goals are in the long run, in conjunction with sometimes changing picture of regulatory standards. Many states are in the process of trying to, or have recently developed nutrient criteria that come into play here as well. But it's just been my experience that goal setting in most cases goes further than that. It's more conservative than what state and federal standards require.
Okay, great. 2 questions, maybe 2 minutes. If you're only sampling during the summer months, would that impact annual concentrations? Or is it best to focus TMDLs only on seasonal loadings?
I think the best way to answer this. I think what we want to understand are the conditions during the height of the growing season. That's what we're collecting, and that's the data that we're focusing on. Those are the conditions that we're basing our goal setting on. We're often trying to look at those peak concentrations that are happening during that, mid to late summer period, sometimes midsummer, even into, pushing into the first week or two of September, depending on, geographically where you're located. So I'm not 100% certain that I'm answering the question, but as I mentioned, the data that we're looking at and the conditions that we're trying to model are those peak summer conditions.
Great. And one last question. For reservoirs, 2 rivers with a dam and a drinking water intake, is there a minimum retention time to define lakes?
A minimum to define lakes, meaning, boy, I'm not really sure I understand the question. Well, minimum retention time. I mean, I've worked on reservoirs that are gigantically huge and very deep, and some that are extremely shallow and not so big because they're sort of at the end of a run where the water, the public drinking water intake is. So I'm not sure. Maybe the person who posted the question can clarify what they mean by minimum size. Oh, can they turn over too quick to be a lake? Yeah, well, that's the term lake and pond is kind of a, at least in New England, I'm not sure about the rest of the country, but usually something is named as a lake based on whoever first named it and put it on a map. There are some really big and really deep ponds. They're truly lakes, using our, like the diagram here, they thermally stratified, they behave like lakes. There are also some water bodies that are named lakes that are 2 acres in size, and they're not more than 10 feet deep. So it's really just a naming convention. what you really want to understand is it big enough and deep enough to thermally stratify and to have internal load because of anoxia at the sediment level?
Okay. So Bob, thank you, Bob, for setting the stage for all this stuff and giving all the background on just lakes in general. And now we'll kind of dive into the modeling. So the idea here is I'll give just a really quick overview of a general modeling approach, probably about 10 minutes. Then we'll get into the lake loading response model stuff. So we'll do a little introduction, we'll do a demo, and then we'll go into, kind of an example lake loading response model. So with that, I will dive in. So as Bob mentioned earlier, with modeling, people think that when you do a model, it's just a really simple straight line. You start the model, you end it, but it really looks like it's usually a pretty meandering path to get there. So lots of assumptions and testing to get the answer. And then, famous statistician George Box said, essentially all models are wrong, but some are useful. So just going into a couple of different water quality model types. So you have your receiving water models, watershed loading models like the lake loading response model, and then a combination of both. So, really like the receiving water, that's going to tell you what is happening in the receiving water, whereas the loading model is telling you how much is getting into that water body. And the combination can do both. So in general, the lake loading response model, you could consider that a combination model, but there's other models that are a bit more nuanced than that. So like, for example, bathtub is a really widely known receiving water model. And then a combination of both, could be like EPA's SWIM. Models can be empirical, so based on statistics, or they can be deterministic or mechanistic, depending on, really just process and equations, or a combination of both. Models can vary in complexity. So there's a lot of models that are just a simple steady state model, which is what the lake loading response model gives you. It's going to give you one answer on an annual average condition, or you can have more complex dynamic models. For example, we can simulate the flow of water over time during a flood. Models can vary spatially, so we can just be looking at a 1D model, like a cross section. Sometimes you want a little bit more resolution. For example, if you're doing a flood model, you want to know not only how high is the water going to get, but where is the water going to extend to. And then we can get into this, the 3D modeling world, where there's all sorts of applications like doing scour analysis. In general, more complicated models will need more data. And when selecting a model for any project, it's going to depend on a lot of different factors. What are you trying to simulate? Are you just doing phosphorus, for example? Are you looking at flooding? Do you want a 1D model or a 2D model? The timing requirements. And then also just available data. So sometimes some models need more data than others. Okay, so we'll breeze through some of these modeling concepts. So I'll talk a bit about data needs, analyzing data, how you can set up model geometry in the inputs and simulations. So I'm going to go through this slide fairly quickly, but Bob pretty much covered this. In general, if you're in the lake loading response model world, it needs a fair amount of data. So you're talking about physical data like hydrography, bathymetry, land use, water quality monitoring is very important to kind of ground truth the model. And then there's always information from the literature, for different parts of the model, like atmospheric deposition. So this data is generally available, so you can get a lot of information from GIS data sets, weather gauges, or from the miscellaneous studies. One thing I always like to talk about is how important it is to compile data properly. So in general, water quality data can come in like a ton of different shapes and sizes. We can have spreadsheets where you've got, every single variable as a column with your site over here. We can, it can basically look a whole bunch of different ways, or as a more structured data set. So I always like to say, we've kind of seen it all when it comes to monitoring data. In general, this best practices for this is just to have a nice uniform format and stick to it. So if you're doing, monitoring over 5 or 10 years, try to keep it nice and simple, make it easy to document changes, and always be able to go back to what the original measurement was and automate if possible. So, and may the source be with you. So always get back to the source. One tool that I've used before is called Tableau, which it's a great little analysis tool. So like one example here is you can use this tool to get all of your raw data. So if you're in Excel or you're just, taking measurements, you can do that, and you can have a bunch of different files. So in this case, I've got 2 files here. You could have 15 files, one for each station, one for each year. And then it's a way to automatically manage your data, so you can join everything up together. And then you can essentially pivot the data, so you basically makes it more analysis friendly. And then one step that I really like is once you have it in this format that you like, you can clean all of your data. So you can change headings, change the number type. Maybe you want to have this with 1 decimal place or 2 decimal places, or group data together into different, monitoring stations or seasons. And the output of this is you hit run and you get a nice, simple CSV file that's going to be the same every single time. And then as you add data, you can add that back into the raw files and have a nice, simple approach. So, and then, once that's done, then everything's ready for analysis. You can use Excel pivot tables or some other kind of software. There's like tons of them coming up now. Over the last 5 years, there's been an explosion of really good analysis tools. Okay, so we'll talk a little bit about model geometry. And this image is taken right from the Lake Loading Response Model user guide, just kind of showing a general example, or I'd say it's a typical example where we have a lake, it's got a watershed. They've classified this into different sub-watersheds that all drain to the lake. Some of these have wetlands, some of them don't. And then in the lake loading response model, we can just simplify this down, into kind of a diagram or a schematic. So that's kind of what we do, is you boil down what's happening in real life into a schematic that can be used for analysis. Some of the inputs that we'll talk about are first on the watershed side of things. So we'll talk about land use data, getting your precipitation data, and then how to route everything through until you get to what is coming out of the tributaries into the lake. And then we're going to start looking at the in-lake modeling side of things, where you take all the loading, talk about the internal loading and the the physical lake characteristics, to finally, at the end of all of this, get some information on what the in-lake water quality looks like. Typically, if there is water quality monitoring data, we will do a calibration of the model. So this is a pretty iterative process where you go through, you see if calibration and validation targets are met, and then keep on adjusting until you kind of are within an acceptable range. And we'll talk about all this. I just want to set the stage now before we go in more detail. So what is a typical outcome of this whole process? So we're going to probably spend the next hour or so kind of going into the weeds, but one of the outcomes of these models is to figure out, if you have a lake, what are the reductions that you need to meet water quality goals? So in this example, we have load on the y-axis and then the resulting in-lake concentration on the x-axis. So this would represent existing conditions of what's been modeled. So let's say we're at 24 micrograms per liter. You can now use this model to figure out how much do you have to reduce loading to get to a goal. And so, for example, if you wanted to go from 24.7 down to 23, you would need an 8.6% reduction in phosphorus. So this one example of how we can use one of these models. Okay, so let's talk about the lake loading response model now. So the lake loading response model, it's just a spreadsheet-based model. It evaluates nutrient loading to lakes. It actually originated as a teaching tool. And it has a bunch of different coefficients that are based on New England specific values, but this can be used in other regions too. There's a lot of different versions of the lake loading response model around. The one that's available on the web is at this link here. So this would give you one version of the model as well as the user guide. And maybe I can paste this into the chat at the end just so folks have this. So some of the advantages of LLRM, it's a really transparent model, so it's not a black box at all. It's all done in Excel. It's pretty user-friendly, and it's customizable. So if you don't like, how it's doing a calculation, it's all in Excel, so it's very easy to tweak if needed. I guess some of the limitations, it's not like your typical, model like EPA SWIM, where it's has a nice, graphical user interface. And it is a fairly simple model, so we're not doing any dynamic routing or anything like that. So it's going to give you a static answer over a whatever analysis range that you're looking at. So we just went over this already, but this is kind of what just an example schematic of how you would turn a watershed into a model. So the typical workflow for LLRM is coming up with the existing conditions model. Hopefully there's some data where you can calibrate that, and then perform load reduction analysis. So figuring out what do you need to meet water quality targets. There's some other applications too. Some of the common ones that we'll do is not only looking at the current in-lake condition, but looking at what would happen if conditions before humans came. So what's the natural background of this? What could happen if this watershed gets built out? What if a bunch of new subdivisions are built? And there's lots of other possibilities here, but those are some common ones. So the typical LLRM inputs are listed out here. So we're looking at rainfall data. That's one of the bigger ones, and it does a lot of its calculations based off precipitation and nutrient export coefficients. So really figuring out how much water is generated in each watershed. And then based on the different land use types, you can figure out, what the export is of nutrients, for example, kilograms, per hectare per year. And then these land use processes are usually the biggest component of loading, but we can also add in other sources as well, like aerial deposition, septic, internal, et cetera. and then it routes everything through until it gets you to the outlet. And once we do all that analysis to get the inputs, then we get into what the outputs are. So LLRM will output your estimated runoff and base flow, nutrient loads, nutrient concentrations, and then we'll get you an overall summary of what's actually going on. What's the resulting load and concentration. So what we'll do today is go through all of these. So starting with inputs, we'll go through kind of all the main inputs that you have to consider when doing an LLRM model. We'll go into the outputs, so how do we get to that in-lake water quality? And then, once you have a model that's working and you trust, then you can start doing some of the analysis and, calibrating it, doing scenario analysis and figuring out, what you want to know about your lake or your water body. So we have a case study here, and what I'll do is we'll kind of introduce each one of these concepts, and then we'll explain how we've done it for one example. So those slides will just be outlined in orange here. So our example watershed is Hood's Pond in New Hampshire. So this, I'm not sure, hopefully this is not too small, but it's a fairly large watershed, about 4,000 acres. Everything drains down to the south to Hood's Pond, which is pretty small. So it has a watershed to lake ratio of 570 to 1. So it's a lot of watershed for a pretty small lake. Bob went into the different types of lakes, but this is a shallow polymictic lake. So it's not going to get those layers that Bob talked about with the epilimnion and the hypolimnion. So it's pretty much, it's mixed. Okay. So Bob had his AI generated images. I've also tried to do that here. It's not bad. It's amazing the last couple of weeks how good this stuff's gotten. When you ask for a sad lake, it's calling. For some reason there's a river here going out of this factory, but other than that, not too bad. So what I'll do now is do a quick demo of LLRM. And Beth, I just wanted to make sure that as I change over to Excel, that folks can still see Excel and not the slides.
I'm seeing Excel.
Okay, awesome. Just wanted to make sure I wasn't just sharing the PowerPoint.
Gotcha.
Okay, so I will do a very quick run through of LLRM. So it's all done in Excel. So it's not a glamorous user interface, but it definitely gets the job done. So in general, it has it set up where anything in blue is going to be a user input. And then anything in tan, you can get these reference variables. So what I'll do is I'll just walk through this really quickly, and then I think that'll hopefully help folks as we go into each one of these inputs in the next set of slides. So what you would do is we start off by entering in our precipitation, and everything is generally done in LLRM on an annual basis. You can play around and just do things during the growing season, for example. So we have done that a few times. So it kind of all depends on what the overall goal is. And then we get into LLRM breaks land use up by these factors here. So we've got urban land for low density all the way to high density and industrial. There's agriculture land uses like row crop and cover crop, forest, including upland and wetland, and then open water. And I'll talk a little bit about how we can kind of modify those land uses based on other data sets. So the first step is just to assign export coefficients for these different land use types. So there is a tab over here called reference variables. Again, this is based on the literature, and it's just been all, summarized essentially. But one example here is, all these different export coefficients for phosphorus. It gives, from the literature, a minimum, median, a mean, and a maximum. So kind of a nice like starting point for some of these models. Then we roll down into other sources of load. So looking into atmospheric deposition, where you can get that from reference variables, internal loading, which we'll talk about a little bit, waterfowl, point sources. Maybe you have a wastewater plant upstream, so there's a way to figure out what the load is from there. Septic systems, and as Bob mentioned, some of these calculations will come into, how many dwellings are there, how many people live there, how much water do they use, per day, and that sort of thing. The next step is doing a GIS analysis to figure out, so you're going to delineate all your watersheds. So in this case, W1 through W11 are sub-watersheds in the Hood's Pond watershed. And you want to figure out what proportion of land use there is in each one of those sub-watersheds, so how much urban land is there versus upland versus wetland, for example. And then LLRM will kind of march through the calculations. And again, what's nice about it is that it's very transparent. So we can just click on any cell, nothing is locked, it's all right there. You can see exactly how the calculations are done. So it will take the information on precipitation retention, as well as how much precip there is per year, to come up with estimated runoff, as well as base flow. And then we get into what is the runoff-based phosphorus versus the base flow generated phosphorus. In general, runoff-based loading is much higher than base flow. We get into routing here. So this is how we can figure out, how the flow goes from one watershed to the next. We take that routing and then we can sum all the drainage areas of these watersheds together. And ultimately, as we scroll down here, start to come up with how much loading is estimated to come out of each individual sub-watershed. And then finally, what's the estimated concentration at the outlet of each sub-watershed? And then what's the overall load summary? So how much atmospheric deposition versus internal loading versus watershed load. And then we go over to the predictions tab and have a couple different things to input here. It's really just based on, really physical characteristics of the lake, like what is the area, what is the average depth. And then it takes a lot of the information from the loading, and you can start to figure out what's going on in the lake. So LLRM just uses a lot of empirical models that have been around and widely used for decades. So like for example, Bull and Whiter, and it will use all of these different relationships, calculate a concentration in the lake, and then you can kind of figure out which one makes the most sense to use an average of them. It doesn't, so all of these are based on fully mixed conditions. There are some other empirical models that can be used, like if you just want to look at the epilimnion on the surface. We could also use this to figure out what the chlorophyll concentration is, Secchi disk transparency, and then bloom probability. So that's a whirlwind right there, but that's kind of what, that's under the hood of what we're working with. And just see how we do it on time. Okay.
Dave, do you want to do a couple questions now or keep going?
We could do that. We could do maybe like 5 minutes of questions.
Yeah, I think there's
sure.
only a few, so they could be related to this session. All right.
Yeah.
All right. So I think you're going to put a link for the user guide when you get a chance.
Yep.
then can you talk about calculating the standard water yield and variations with those estimates?
Yeah, so the standard water yield, we actually have a slide on this, so I won't go into too much detail. But that's just really, what your estimated flow per upstream square mile of the watershed is. So yeah, I'll just leave it at that, and we're going to go into that in a few minutes.
Okey doke. And can you go over the reality checks, please?
Yes, the reality checks part. So there's what's called a reality check here in the model. So that's really all of that is you can actually put in your water quality monitoring data, and you can figure out how close your model output is. So for example, if I were to look at this case, then the model is estimating output of 0.2 milligrams per year. In this case, the reality check is that the measurement is only 0.036. So we'll talk about that during calibration, but obviously this example way off, needs some adjustments.
Okay. And then folks are asking, would it be possible to share this Excel file example with the group?
Yeah, we can do that.
Okay,
Yeah, we can follow up after this.
great. And just one other question, how does the model calculate the internal phosphorus loading?
Yeah, so there's like 4 or 5 different ways that you can do it. So I'll go into that. I have like I think 5 or 6 slides on it because it gets pretty complicated. It's tricky.
Okay. And I now there's a couple more questions, so we got a couple minutes. I may have missed it, but is the model also able to calculate or handle nitrogen loads?
Yes, I did not go over that, but it is set up. I don't know if this version has it because we might have erased it, but as you go through the model, if you scroll over, which is not here, I don't think, but there is a whole separate section for nitrogen calculations. So it does it. I think we just took it out for this example just to make it easier. But yes, it does the nitrogen as well.
All righty. And are there any special considerations to make for areas that are controlled by snowpack instead of annual rainfall?
That's a good question. I do not have a great answer for that.
Okay. Actually found another question in the Q&A. Are there any special, oh no, I'm sorry, that was the same question because I think that person transferred their question over. So thank you. And I think we're good to go, Dave. Thanks.
Okay, sure. All right, now we will get into the model input. So this will probably be the most like technical part of the conversation here. So I'll try to keep everyone awake during all this. Some of these slides might have a bit too much text here, but what I wanted to do is that if someone comes back to the recording, you can actually kind of see what we're thinking. So I'll try not to read all the text. So in general, the first thing to look at is the analysis period. So LLRM does everything on an annual basis. So it's just not like an event-based model where you're going to be able to look at, pollutant loading, from a 24-hour storm. In general, it's suggested, to look at to look over a 10 to 20 year time period. So 10 years kind of gets you enough data to see what's going on a long-term average. Once you get beyond 20 years, some of these lakes can actually change quite a bit. You can have huge changes in loading but in general, 10 to 20 years, but it's going to be site specific. Bob talked a bit about stats, but you can always do an outlier review. The goal here is to get representative annual average conditions. So if you have rainfall with 3 years of drought, you might want to consider removing that if you want to get representative conditions. So it kind of all depends on what the goals are. And we could go into outlier review, as Bob said, probably in another 3-hour training. But suffice to say, so like here's one example of outlier review where here we've got precip data for 10 years. So we have our y-axis is precip, x-axis is the year. So we can see here we've got some really high rainfall in 2011, really low rainfall in 2016. These are outlier years. You could take these out. Kind of all depends. If you have a long enough sample set, it'll end up smoothing out over time anyways. So Hood's Pond, our case study example here, we had data available from 2014 through 2023. Not a ton of water quality data, so looking at about 14 samples in what we call the in-lake portion, with the median total phosphorus of 27, and then we had just a few tributary samples, so 7 and 5 here, with so what we ended up doing is going with a 20-year precip model evaluation year. You can make the argument to just do this based on where you have water quality data available as well. Okay, so how do you get precipitation data? There's a couple different sources here. What I've used over the years is the NOAA Climate Data Center. So it's got a nice, interface where you can zoom into your site, and figure out, what station is closest. Ideally, you'd have at least 10 years of rainfall data. Other options, you can, you could use local gauges, weather underground, for example, and just have to make sure that that data source has been QC'd. So in this example, pretty straightforward. We have 20 years of rainfall data, and we've got a nice table. So what goes into LLRM is this average of 1.04 meters. Okay, so reference values. So LLRM has that reference value or variable tab for a lot of different model inputs. So they're based on the scientific literature. They typically use them in general ranges, so like for the pollutant load export, high, medium, low. And these can be replaced with anything, so like we've used in Massachusetts and New Hampshire some of the 2016 MS4 pollutant load export rates, for example. So it's very modifiable, but it does help you kind of get to the answer fairly quickly. For example, with like waterfowl loading, you can see there's some estimates of how many kilograms per year an individual bird could export. So our export coefficients for land use types, these are split into runoff versus base flow coefficients. And I'll just jump into some of the examples here. I think it'll be easier to visualize. So we've got all of our land use. And in general, these precipitation coefficients, this is going to impact how much runoff leaves each watershed. And then these phosphorus export coefficients are going to impact how much phosphorus would be exported off of each land use type. So for example, for low density residential, we're talking about 0.8 kilograms per hectare per year. What we typically would do in a model is, before doing any calibration, just start with the median value. But if you have other information of the watershed, knowing that it's got potential high loading, you could go on the higher end of things too. But as we'll see, you kind of just want to get the model built in the bare bones first, and then you can tweak things as you go. The other, there's other calculations here as well, so you can look at aerial deposition, internal loading, I'll go into. Most of these do have reference values that, we can use, so for example, the waterfowl has a median of 0.2 kilograms per year per bird. So if you know that you've got a watershed and maybe there's like a flock of geese that nest right next to the lake, and maybe someone's done some observations there and figured out that there's 500 of them, that could be a pretty significant source of loading, depending on how big the watershed is. Okay, internal loading. So as Bob mentioned, this internal loading is really the nutrient cycling from bottom sediments, and it can vary widely. So some water bodies, it could be a huge proportion of loading. Others, it could be a very small fraction. So in general, what we do is, to calculate internal loading is hopefully there's some available data, and we can put that into the initial model and then kind of check the output for reasonability and then just adjust during calibration. So I'll talk about this a bit more in detail, but the proportions of loading are sometimes tough to get in these models if you don't have really good water quality monitoring data for the tributaries as well as the lake. So I'll talk about that in a bit more detail. But there's a bunch of different ways that one could calculate internal load. So you can do water column sampling. So essentially getting samples at the epilimnion down to the hypolimnion at the bottom. You could do sediment sampling to figure out what a release rate is, and then there's some other ways as well. So I'll just go into some examples here. So one example is water column calculation. So this is really more for like a deep water body that could be stratified into a epilimnion, versus a hypolimnion. So the way this is done is calculating the difference in concentrations at the bottom of the lake over time. So essentially at the beginning of the growing season, and then towards the end of the growing season, once the water quality starts to get worse, and then you can do some calculations to come up with what the estimated internal load is. So what this looks like in this table is that we're looking at the hypolimnetic total phosphorus concentration in May, so before things start getting bad. So we're at 21 micrograms per liter, and then we get to the highest point of total phosphorus down at the bottom of the lake in August, all the way up to 173. So you can kind of use that figure and then do some math to figure out what the accumulated phosphorus concentration is, how big the hypolimnion is, and come up with an estimated internal load. That's probably the most complicated way to do it. There's certainly easier ways to do it. Some other examples, which might be more, might work better for a shallow water body like a mill pond, or actually our example in Foots Pond could work well, is to simply compare the difference of phosphorus between the inlet to the lake and the outlet to the lake. And then figure out, what the typical outflow is, and then you can get a rough estimate of internal load. So how that would work in actuality here is we can imagine that we have a pond. So the incoming phosphorus might be 35. At the outlet, it's 95. So a pretty big difference there. So that's a lot of that is probably attributed to internal loading. So we can just simply take the concentration times the estimated flow to get an estimated load. And again, so these first two examples are probably the more complicated ones. Now we can just get into actually using some of the reference value variables from LLRM. So one thing you can do is use the sediment sampling results, and that'll get you a release rate, of milligrams per meter squared per day. And LLRM has a reference range here, so it could be anywhere from 0.1 to 40 with a median of 2. In the case of Hood's Pond, we used the LLRM reference range. So, this is a polymictic lake, relatively shallow. So we basically took this reference range, which is estimated as 0.1 to 10, and simply multiply that by the lake area to get an estimated load. So, estimating that you're at the median range, so 1 kilogram per hectare per year, multiplied by the lake area, 2.46, and you get about 2.5 kilograms per year. And then you can adjust this more during the calibration process. So that's kind of like the whirlwind tour of internal load. This is always one of the sticking points in all these models. Every single lake is different, and it can be fairly tricky depending on how much water quality data and flow data there is available. And then one thing that I'll go into in more detail is that, if you're going to use this approach without actual data, you do, want to have some confidence in the external loading, that's coming into the lake from the tributaries, or else you could end up with the right answer, so the right in-lake concentration, but the proportions can be off. So you might, think that there's more internal load relative to what's actually happening, or vice versa. Okay, so now we'll get into delineations. Let's do a quick time check here. Still doing okay. Okay. So delineations, there's a lot of really good tools now, for figuring out the overall watershed and the sub-watersheds that make up that watershed. So StreamStats has been around, for quite some time. It's still a great tool where you can essentially just click on any point and figure out what the upstream watershed is. So the only caveat to this approach is that it is only based on topography. I have heard that there's a rumor that they might be starting to do a pilot looking at, stormwater networks, for example, to incorporate those. But right now it's just based on topography. So it does, require some judgment, to adjust boundaries if you know that there's, a drainage system in there, or if something just looks wacky. And then, once the watersheds are delineated, you can use GIS tools, to figure out, how big each sub-watershed is and what the land use is. One thing just to note is that when you are delineating a watershed, you want to make sure to take the lake out of there, because the loading onto the lake is going to be estimated through aerial deposition. So you do want to have the area around the lake, so the proximal watershed, but you want to take the lake out, since we're calculating loading to the lake. And this slide here is showing an example of our case study. So we have our watershed here. Hood's Pond is kind of down on the south here. So we've split this up into about 10 or so, I guess 11 sub-watersheds. So we can see, how this works. Kind of everything kind of flows down, everything joins together and gets in there. And then Hood's Pond has 2 tributaries. One is most of the flow, and then there's a small one to the northeast. And the resolution of this can vary widely. So in general, what you want to do is try to get at least where any tributary joins in. So like in this case, this stream joins with this stream, so that's a good spot to have your own sub-watershed. Scobie Pond here joins in with Shields Brook here, so that's a good logical spot. But you could do this even more at a more fine resolution, depending on modeling goals. All right, so land use data. Once the watersheds and sub-watersheds are delineated, we can then use land use calculations, to calculate all the runoff, base flow, and pollutant loading. So all this is just based on those runoff and pollutant load export coefficients. And like one example here is that agricultural land use, would generally be expected to generate more load than, say, a forest. One thing I did want to go over here is LLRM has their very specific land use classifications. So these are just some examples, not all of them, but we have, urban, low density residential, up to medium to high. There's some agriculture. In general, land use data can be in many different forms, and it usually doesn't, it's not like an apples to apples comparison. So it usually does require some kind of a lookup table to convert whatever land use data set you're using into these LLRM classifications. So like one example is, we oftentimes use the National Land Cover database, which is available across the US. So it just requires a lookup table to say, okay, LLRM is calling this low density residential. How am I going to map that to the NLCD? So this map is just showing an example of land use. This is a different watershed in New Hampshire, but in general, we've got our forest is in green. Any urban area or developed area is in red, and agriculture would be in yellow. And then we'll put this into a table, and we can figure out, in each one of these delineated subwatersheds, what proportion of land use is there. So how many hectares of developed area is there in the subwatershed versus forest versus agricultural. Okay, so routing. So we can route based on tributary. So routing is done in LLRM. It's not like super intuitive, so it takes it. This always makes my head go a bit fuzzy when I'm doing routing. But the way that it works in this example, we have our lake here, Bantam Lake. So we've got one of these subwatersheds, W2, goes right into Bantam Lake. And then in this case, there's some routing here where W5 goes into W3, for example. So you can assign if a watershed passes through another just based on a 1 or a 0. So if it does not pass through another subwatershed, you input it as a 0. So in the case of Bantam Lake, it's not going through anything. The same thing with W2, that's just going right to the lake. But you would want to do some routing for W4 and W5 because they are going into W3 before they go into Bantam Lake. So kind of a complicated, it can get complicated, but once you kind of look at the table, it's usually pretty easy to get it straightened out. And then one just QC check is when doing routing, you can always make sure that the cumulative areas match. So if you know what the overall watershed area is, make sure that when you're doing the routing that everything lines up, and you'll know that it's then represented correctly. Okay, how am I doing on time? Okay, yeah, I'm almost done. Probably just a few more slides here. Probably. Okay. So attenuation, Bob went through this, so I'm going to kind of breeze through this fairly quickly, but LLRM has some attenuation guidance, so looking at about 5 to 15% for water attenuation. So as, flow passes through wetlands, for example, it can be absorbed, infiltrated, that kind of thing. So, usually about 5 to 15%. And then pollutants can be, it's usually a higher number. So anywhere from 10 to 60% removal. This will vary widely based on watershed And this is all very high level stuff. So we're not getting super into the weeds on anything here. So in general, you want to assign attenuation just based on best judgment and any available data. One way that we've done it in the past is looking at, just the overall visible attenuation features in a subwatershed. So like, for example, if we're looking at this Bantam Lake watershed on the right, we could try to assign, if there's a small amount of wetlands, maybe 10% of those nutrients could be retained versus large, maybe 20% can be retained. And again, this can all be adjusted during calibration, but just as a starting point. So like in this case, W7, so in this case, wetlands would be classified as this light green color. So W7 has very few wetlands, so we give that a small attenuation factor. W4 is got a bit more, so maybe we call that medium. And then W3 is mostly all wetlands, so we give that a larger extent. Flow attenuation is the same exact thing, so the one thing I would say here is that sometimes there is tributary flow data available. So at the outlet of each tributary, and you can see if your estimated outflow matches up with anything measured. If not, LLRM does incorporate the standard water yield. So again, this can vary like widely for different watersheds, but it's a good kind of just a rule of thumb or a very coarse estimate of how much flow on average could be generated. So in general, the standard water yield in New England is 1.5 to 2 CFS per upstream square mile. So it's a really simple approach, figuring out, on average, depending on your watershed area, how much flow can you generate. You could also use stream stats, as another estimate, so again, you just have to know that it's it's not based on any actual measurements, it's just an estimate. In general, if you're within about 10%, you know that you're pretty close at least. Okay, so one thing to note with LLRM, or at least the version of LLRM that we've used, is when you have what's called triple nested watersheds, sometimes the attenuation breaks down. So what we found is if you have more than 3 watersheds that go into another, there's something funky that happens in the model. So we've done a bit of a site analysis to get around that. So Bob went into this already, so I think I'm just going to breeze through this example here, but this just kind of shows how LLRM handles attenuation. So it's very simplistic, so if we just had a really simple example where all of these watersheds generated 10 kilograms per year, which again, probably would never happen, but just to keep it simple. And if they all attenuated about 1/10 of that, we can kind of march down here and show how the calculation is done, so 10 times 0.9 is 9, then you get to the next one, you're adding another 10 to that 9 to get to 17.1, and so on and so forth. So in this case, you've got 5 watersheds, they would generate 50 kilograms of total load, but by the time that gets to the lake, it's 36.9. So other models, are more, they would actually simulate this, like for example, SWIM, but LLRM, it's just a simple attenuation factor that you can apply to each one of these subwatersheds. So in this example here, there's just a little side analysis that you can do. So it takes a bit of manual effort, where you'd actually have to kind of draw in your routing to figure out, where everything is going. And, once you've kind of got that site analysis done, and again, we can share some examples of this, then that can just be input right back into LLRM. So this kind of goes to one of the advantages of LLRM, that if something is not quite working right, there's always a workaround because it's not just a black box. So in our example here, in Hood's Pond, I won't go into all the details here, but in general, our pond is down here. So everything goes into it except for that one sub-watershed over on the right. You can also use this approach to attenuate septic loads. Okay, and one thing that we usually do in these models is we will not assign attenuation unless we have really strong reason to, until the calibration process. So we like to just get the model working, get everything figured out, and then start to turn the dials of attenuation during the calibration process. Okay, and that's it. So we can do some questions and then take a little break.
All right, Dave. So like maybe 5 minutes for questions, considering we do have some time blocked out at the end for questions as
Yeah,
well.
that
Okay.
sounds good.
Sounds good. Thanks. Is there a minimum watershed size to run the model?
I don't think so. No, I mean, I'm not sure if the guidance has anything on that, but I think you can use this on fairly small systems, like, I don't know, I'll just throw a number out there, but 5 acres, probably work okay.
Okay. Any thoughts on the advisability of using gridded precipitation product for LLRM, like NOAA's DAMIT data releases?
Yeah, or like Prism used to be one that I used way back when. I don't see why not. I guess I would leave that as a like, probably. I just have to think about it more.
Okay. What is the difference between runoff and base flow?
Yeah, so in LLRM, there's the runoff, and that is anything being exported during an active precipitation event. Yes, that could be flow or nutrients, and then the base flow would be when it's when there's no runoff, so when everything is dry.
Okay. Do the land use export coefficients account for soil type or land slope?
Let me just look really quick. I think there is a little bit of that in there. But in general, what they do is they'll give, a minimum, a median, a maximum, and a mean. So it's kind of up to the modeler to say, okay, maybe this watershed, with the steeper slope, might have a higher export. So no, I don't think it actually does go into that level of detail.
And for flow attenuation by wetlands, how do you estimate what proportion of the flow from a watershed goes through a given wetland?
Yeah, so it's just going to be based on professional judgment. And so if you have tributary monitoring, that's the best case scenario where you actually know what your outflow is. But in general, you can use the standard water yield to make sure that you're at least within a rule of thumb estimate. Yeah, you would need monitoring data if you really wanted to get that tightened up.
Okay. I have seen several final LLRMs for New Hampshire set internal loading of phosphorus to 0 based on lakes like Hood being shallow and non-stratified or lack of data. I get it for keeping it simple. Seems like an oversimplification. Is this problematic for past TMDLs, or can this be justified?
Hmm. Yeah, that's tricky. I think in general, it's going to be really lake specific. Like what we'll go into with hoods is if you have good tributary monitoring data and in lake monitoring data, you can kind of use those to figure out if the lake does indeed generate internal load. Otherwise, it does get really tricky, where we'll talk about this, where you might have a model that is calibrated and you're estimating the in-lake concentration, but you could have the proportion of loading off, from internal to the land use based loading. So yeah, it's a good and a tricky question that we grapple with all the time. So now that we've gone into all the different model inputs, now we can start talking about what does the model actually output? And then how can we actually start to use this? So we've gone into all the different nuances of coefficients and land use data. Now we can maybe have some more fun. So what outputs does LLRM give us? So we're going to be able to figure out watershed loading from LLRM from each one of those delineated sub-watersheds, and also just loading from those other different sources that we talked about. So, if you have septic loading versus waterfowl versus internal loading, and then we can get into the in-lake side of things and start to figure out, what is your in-lake water quality? What are your potential total phosphorus concentrations? What's your probability of having an algal bloom? So, for example, in our case study lake here, this is showing all the different loading by source that go into Hood's Pond. So, we ended up with the land use loading generally takes up the largest portion of loading. In most cases, sometimes internal load, will take up a lot more, but we have about 62% land use. We can, have some internal loading. Waterfowl is a fairly large proportion, and then septics. So that's one thing that we can look at is, what is causing the issue, and then that can help figure out, okay, what management techniques are needed to start to minimize this loading. Do I need to focus on septic systems, versus, watershed scale BMPs? So same thing, we can look at, loading based on land use. So I think Bob went over this already, so I'll do this fairly quickly, but in general, we can look at, in this example for the Bantam Lake watershed, this pie chart here on the top is showing the overall area of the watershed based on land use. So, about 60% is forested and only 9% is urbanized. But when you use those pollutant export rates, a larger proportion is going to be generated, for example, by the urban land uses and the agriculture than by forest. So just a nice simple way to show where the where the loading is coming from based on land use. We can estimate, what the potential loading is by tributary. So in this case, we only have 3, inputs going into Bantam Lake. It's going to be the proximal watershed around Bantam Lake. It's going to be this Whittlesey Brook over to the south. And then the main tributary is all this stuff in red here. So that's most of the loading. So this is a bit more interesting, for some other lakes, which need, have more sources, or so that's one way to look at it. One other thing that you can do is you can plot everything out on a map. So this is probably a bit too small for people to see, but we can show how much loading each sub-watershed actually generates, and then what the estimated concentration is at the outlet each subwatershed. So, we can kind of see here that, the headwaters here, our estimated concentration is 20 micrograms per liter. And then as we march down, it starts to go up a little bit more, 26 up to 34. So it's a nice way to track and see, where the problem is starting to occur. Okay, so now we'll talk a little bit about the in-lake water quality calculations. So LLRM just uses these, essentially models or empirical relationships, that have been built, that have been used for many years. So we can come up with estimated in-lake water quality for total phosphorus, chlorophyll A, Secchi disc, and algal bloom. And in general, each one is predicted based on multiple models. So you can, some people have a preference over which one to use. Sometimes it makes sense to use one model over another for a specific lake. So in general, the advice is to pick the model that fits the characteristics of the lake the best. In general, LLRM will feed in most of the inputs that are necessary to do the in-lake water quality calculations. So really the big ones are just the physical characteristics of the lake. So what is the overall surface area of the lake? What's the estimated average depth and the volume? And then you can usually get your in-lake water quality calculation. So it's a nice, simple way to get calculations quickly. So these are the total phosphorus prediction models. So we've got Bohlenweider, from 1975. Bachman is in there, Breckow, and as we can see just in this example, they all give very different estimates. And so sometimes it makes sense to choose one of these. Other times you can take an average of all of them, and it's just kind of up to the modeler. But it's a nice way to kind of look at all of them and see which one is over predicting versus under predicting, for example. Just a really important note here too, these models are all based on fully mixed conditions. So this means that the water column it's not stratified. So there are other ways to get at the epilimnetic concentration. So in some cases, we have done these analyses where we'll use these models for fully mixed conditions, then have another side analysis, which looks at the epilimnetic concentration. Because I know sometimes targets are set not based on fully mixed, but they're based on the epilimnion. And I'm blanking on the name of the model that we use, but it'll probably come to me. You can also get to algal bloom results. So typically, once you have your inputs necessary to do the total phosphorus computations, those are just carry over into estimates for chlorophyll A, which can then be used to get to the estimated algal bloom probability. So the way, and the algal bloom probability is based on Walker, who developed the bathtub model, back in the 80s. So in this example, there's classifications here. So if your chlorophyll A concentration is in the 10 microgram per liter range, you're into like you're in the scum evident bucket. Whereas if you get up into the 30s, then it's going to be severe nuisance conditions and lots of issues all the time. Okay, so we'll go into the calibration, and then we'll have some time for questions at the end. Okay, so once you go through all this effort, you get all your inputs, you do some initial assumptions, you figure out what reference values you want to use. Then it's all about, okay, let's see what we can do to tweak this model and make sure everything makes sense. So this is just kind of a checklist of quality checks that you can do. Are the reference values reasonable? Did I, keep everything within a reasonable range? I'm not way too high or too low. Does everything actually sum up properly? So if I know that my watershed is, 5 square miles, do all the areas of my routed watershed sum up to be 5 square miles? Did I use, logic when coming up with the attenuated values? And then most importantly, do the model predictions approximate actual data, so either flow monitoring data or water quality data. In general, every model that I've ever built, like the preliminary estimate is way off. It could be off by 100%. You could be estimating an in-lake concentration of 100 micrograms per liter, when in actuality your data is telling you it's closer to 40. So calibration is important. So here's our example here for our Hood's Pond case study. So we estimated that the in-lake concentration was 108 micrograms per liter as compared to an observed value of 27.5. So obviously calibrations needed here are tributary concentrations up in the hundreds, in the 200s as compared to 24 and 40. So calibration is needed. So again, this is where there's this straight line of success, but really when you're doing a model, you kind of have to go back and revisit assumptions and turn some dials, to make things represent what's actually happening out there. So the model calibration process is, first of all, to figure out, do you have enough data to do validation? So I'll talk about that in a little bit, but calibration is, actually, no, I think I have some slides on that. So I'll just hold off on the validation. So you want to figure out what time periods you want to calibrate your model, figure out what an acceptable % error is, for your project, adjust the model as needed. And then we can look at it during calibration. And then if you have enough data, you can consider validating the model as well. And validating the model is really just running your calibrated model and making sure that your % error still stays within acceptable ranges. Yeah, so if you have the data, validation is recommended. It's oftentimes in these models, there's not enough data to do this, but it's always a bonus. So if you were to do calibration, this is this one example here. Let's say that we have, what is this, 10 years of data or more. And let's say that, all the data is pretty decent. You could say, I'm going to calibrate from 2006 all the way to 2016. I think we took out some outlier years here. And then I'm going to use these last 2 years of data to validate that. So once I think my model is calibrated, I've turned all the knobs, now I'm going to validate and just run it as is and make sure that everything actually still works. So sometimes you'll find that you've calibrated it and it looks great for the data from 2007 to 2015. Then you try to validate it and everything falls apart and you got to kind of try again. Whoops. So this table is just showing some rough examples of what a calibration target could be. Forget what study this is from. I probably should have cited that here. I think it was from, I want to say Donegan. But in general, if you're within 15%, that's typically, that could be very good, as opposed to 25 to 35%, you might have a fair outcome. So this can vary depending on project. Some targets might be much more strict than that, especially if you have a lot of data. So if you have years and years of water quality data, I would be much more strict at these targets, and I would say that you want to get within 5%, to have a very good calibration. Okay, so there's a couple things that you can do during the calibration process to tweak your loading estimates. So the first thing is, we're going to look at our, if we have any data, we're going to look at our flow data and water quality concentration. So this could be tributary outflow going into a lake. This could be the in-lake concentration for water quality. We're going to compare these to the predictions from LLRM and then start to adjust things. So typically the knobs that you can adjust the easiest are those flow and nutrient attenuation factors, as well as the export coefficients. And then kind of on the side, there's also some other adjustments that can be made too. For example, if waterfowl is a big factor, you might want to adjust the amount of export per bird or some of the septic variables. So really, the whole goal here during calibration is to meet whatever targets you set for the project. And then just make sure that the adjustments make logical sense. So what you don't want to do is just go and make a bunch of changes without having a rational reason for doing that. So here's an example of Hood's Pond where we applied the attenuation factors during the calibration process. So looking at this based on the proportion of visible wetlands, that we can see based on imagery and land use data, so keeping it very consistent, having, so if you've got, moderate attenuation, we were at factor 0.9 versus 0.95 for low versus 0.85 for high. So what you don't want to do is just go in here and just have a bunch of random numbers. So you want to have some kind of logical basis for whatever adjustments you're making. The other thing that can really change the model outputs are these land use based export coefficients. So this table here is just showing what the reference values are. So for example, for urban 1, which is low density residential, the reference variables could be anywhere from 0.19 kilograms per hectare per year, all the way to 6.2. So this is, order of magnitude, a huge range. So it just all depends. Are you, is it a really urban environment? So that's why the range is so big. So what we end up trying to do is, we'll usually start off with, somewhere around the median value, and then we'll try to adjust relatively consistently, so, reduce by a specific percent change, for example, across similar land uses. So in this case, I think, we had to go a lot lower than the median, down 80%, for example, until we started to get closer to those calibration targets. So once we have gone through those LLRM tributary inputs, making tweaks to potential loading estimates, then we can get to the in-lake side of things, where we can look at our in-lake water quality observations versus predictions. And then we're going to start to look at our internal loading. We can start to look at the different water quality models, so as we went over, there's like 6 different models that we can look at, make sure that, we've got our physical characteristics correct, and then start to go from there. And again, the goal is to meet the targets and then make adjustments that are reasonable. So in our example here, we have, let's see, there's a lot of text here, so I'll try to break it down. But what we have here in our table is this first row here is our in-lake calibration. So our observed in-lake concentration is about 27.5 micrograms per liter. Not a ton of samples, but it's what we have to work with. We estimated 108.6. After doing some tweaks, we got down to 27.2. So we're really close. We're within just 1%. And then we can look at our tributaries. So again, it's really important to make sure that we're at least close on kind of all legs of the stool here. So now we can check our tributaries. So we're a little bit farther off on the tributaries, but still within 10%. And again, we only have 7 and 5 samples. So as Bob said, we're kind of underneath the threshold here. But as you'll find with lake modeling, you kind of have to use what you have. So when we were working through this, this is just showing the end results, but as you're calibrating, you're doing a bunch of different iterations. And what we were finding during this example is that we had our tributary concentrations pretty close, within 10%, but the in-lake concentration was still way too low. So that's where we can start to play with the internal loading to try to make up that difference and get these as close as possible to what we're seeing in the monitoring data. So what if you're missing tributary water quality data, or if you don't, have any measurements for internal load? So you don't have any sediment samples where you can get the release rate, or any water column samples where you can start to look at, the difference in hypolimnetic concentrations. It is kind of a stool here, where, to be the most confident in your model, you want to have confidence in the tributary loading, the internal loading, and your in-lake concentrations. So if you are missing something, you can still calibrate your in-lake water quality data. You're going to still have confidence in the in-lake predictions, but what you will not know is the proportion of loading sources. So that's where the big uncertainty is going to lie in this. So you'll have confidence that your model is close on the in-lake concentration, but you won't know, is most of this coming from the watershed or internal or other sources like septic. So in general, sometimes when you do a model, you have to document all your assumptions and talk about future data needs. So if you want to increase the confidence in those model estimates. If there is adequate data to validate your model, it's always recommended. So like one example is, let's say that we have really good water quality monitoring data for 15 years. We would do that whole entire calibration process for the first 12 years of that data. And then we could just validate, just for the last 3 or so, just to make sure that it still stands up. So really all that validation is, you're taking your calibrated model and you're running it on an independent data set and making sure that the results are still within reason. So, and then sometimes you'll find that your calibrated model is looking great. You're within all your reasonable ranges, and then you validate and everything goes out the window and you're off by 40%. Then it's time to do some more tweaks to the model. So just one example of what validation would look like here. So just looking at in-lake total phosphorus concentrations, we've got our calibration time period here from 2007 to 2016, where we, turned all the dials. So we were at a percent difference of 4.2. We then reran this model for independent data that had not been calibrated in 2017 and 2018, and got a percent difference of negative 6.6. So we're still within that, goodness of fit range, of 15%. We had kind of a wild swing here from 4 to negative 6. So you can see how just a couple of years of different data can change. Okay, so Ron Swanson, the swamp monster, wants to know, what is the point of all of this modeling? What are we doing all these inputs for? And really so I'll just go over some of like the most common uses for these models. So we can use our calibrated or validated model to start looking at different scenarios. So some questions that we can answer with these models are, what load reductions do I need to meet water quality goals? What did the water body look like under pre-development conditions? And then what would happen if this watershed got built out? What are some, how much worse could the in-lake concentration get? How much worse could the algal blooms get? So the load reduction analysis is really just to figure out what load reductions are required to meet your water quality targets. So Bob talked about water quality targets, which is a whole thing in itself. Every lake is different. But in general, what you want to do is you have your model. You can run your model iteratively now. So you have your existing conditions, and now you can adjust your inputs for low loading to high loading, and then come up with a relationship of load versus concentration. So what that looks like is here where we have our load on the y-axis and our in-lake concentration on the x-axis. And then we can see, what's going to happen if we have really low tributary loading. Maybe we change all of our land use to forest versus higher tributary loading. And then we can actually use that to develop, some estimates of what do you need, what kind of reductions do you need to meet water quality goals. So in the Hood's Pond example, the existing conditions, were about 300 kilograms per year of loading, which resulted in an in-lake concentration of 34. So that's above the generally accepted eutrophic level. We ended up with a goal of 25 micrograms per liter. So in order to get down to 25 micrograms per liter, we would need a reduction of 74 kilograms per year of phosphorus, or about a quarter of all the loading to the lake. Other things that you can do with these models, you can do a pre-development analysis, just to see, what are the potential background conditions, so before we started to build out these watersheds. The easiest way to do this is just take all the land uses and you can change that over to forest, wetland, or water, and consider internal load is insignificant. In some cases, it's, maybe that's not the best assumption in all cases, but in general. You can also do a build-out analysis. This is a bit more complicated, but you can do a build-out to estimate the impacts of new development. There's a lot of different ways to do this. In general, you can look at population projections to get an idea of how land use could change. We've done this on a smaller scale where you're looking at possible buildable lots within a watershed. And then, of course, adding in, septic loading, for those potential buildable lots. And then there's some tweaks that you can make to internal loading, which would presumably increase as build out and tributary loading increases, because it's kind of a feedback loop. So, in Hood's Pond, this is showing an example of how these different sources of loading changed for each of these different scenarios. So looking at pre-development conditions versus existing conditions to build out. So really just like looking at how the proportion changes. So in this case, pre-development conditions, the watershed load made up about 77%, and then it gets down into the 60s during existing and build out, because internal load starts to become a factor here. And then, what this ended up for Hood's Pond is that under pre-development conditions, we're at 9.5 versus existing conditions that really jumped up into 27.2. And with that, we can answer some questions.
Okay, great. And if there are any more out there, please type those into the chat. There are only a few from this last segment. Someone confirmed that Donegan was the reference You were correct.
Okay. Great.
There's a lot of people paying attention here. Could you review again the physical meaning of the runoff export coefficient?
Yeah, yeah. So the runoff export coefficient is so that's the precipitation runoff export coefficient. Yeah, so there's two different runoff export coefficients. There's the precipitation coefficient, and that's really the fraction of precipitation that is going to run off, during wet weather. And then there's the phosphorus or the nitrogen export coefficient, which should be, the estimated loading during wet weather. So for example, for, like urban low density residential, would be 1 kilogram per hectare per year.
Okay, great. And could you review attenuation? I thought earlier you said it was typically 10 to 60%, but your table showed 85 to 90 and maybe 95 for a watershed?
Yeah, so that table would be flipped. So the 85 would be 15% is being attenuated, and 15, 10%, and 5%. Yeah, so but yeah, in general, 10 to 60 is a pretty good estimate. Maybe we should have said 5, 5 to 60, because sometimes there's very little attenuation, especially on a smaller subwatershed.
Okay, and one of the comments, great presentation. Does the model apply attenuation to point source loads input in subwatersheds?
Yes, yeah. So the way it works is, like if you have a wastewater treatment plant, you can figure out what loading that's generating, and there's a whole bunch of ways to do that, especially if you have data, and then you can tell LLRM which subwatershed that load is being dumped into, and then that's nice because then you can attenuate that through all the different subwatersheds.
Okay. And on the last slide or table, why didn't the internal load kilograms phosphorus increase from current conditions to build out conditions?
Let's see. Oops. I think I don't remember exactly what we ended up with this, but I'm wondering if it was just such a small change. I think in this case, it was a pretty small, um, we went from 144 kilograms to 146. So I think we just probably made the assumption that it probably wasn't worth changing that dial. But yeah, I think in actuality, maybe it would have gone up by a fraction. No, I just want to say thank you for sticking with us for 3 hours. There's tons of information, and it's a pretty complicated topic, so every lake watershed model I've ever done, I always go into it thinking I know exactly what to do, and there's always something that you're like, ooh, how do I handle that situation? So it's tricky, but it's fun.
Yeah, it was a lot of information, but I think a lot of people learned from you. So we do appreciate you for doing this, and thanks everyone again for joining us today. I think that's it.